The objective of this lab is to analyze the motion of a falling slinky, creating and manipulating a model that uses the momentum principle to predict how the slinky will fall after being held at equilibrium. I then used VPython to create a model that would compare the predicted motion and the observed motion to determine if the bottom of the slinky does in fact stay stationary during the fall. The lab produced the results that the bottommost part of the slinky does remain less until the entire slinky is fully compressed and continues falling as a point particle system would. The model also proves to be effective at predicting the motion of the slinky. I first used Tracker to analyze a video clip of a slinky hanging at equilibrium and then released and allowed to fall. I set the origin of the coordinate system to be the top of the slinky, where it is held by the hand until dropped. I then calibrated the axis length using the known length of the relaxed spring, 1.5 meters. I gathered 3 sets of measurements until time was 3.1313, which was half a second after the spring had fully compressed. The sets of measurements were the position values for the top of the slinky, the center of mass, and the bottom of the slinky. I outputted these data points and then plotted them against time to get an idea of how the y-coordinates change during the course of the fall. In order to model the falling slinky, I defined 14 masses to represent the slinky as a whole. For each mass, this while loop calculates the distance between each mass in relation to each other, and then uses this calculated value as well as the stretch for each spring, and the provided value for stiffness to calculate a force. Using Newton's second law, the total force acting upon each mass is composed of the 2 spring forces of the masses above and below, as well as the force of gravity. Here's where the momentum principle comes into play. When the net force is calculated, this value, calculated here, can be used to update the momentum of each mass, and then used to update the position. When running this model, you will see that the slinky secured by a force at the top is allowed to settle to an equilibrium position. You can see the base and center of mass of the slinky oscillates until coming to a stop. Then, after the slinky is allowed to equilibrate, 2.5 seconds pass before the force of the slinky goes away, or the hand lets go and the slinky falls. This while loop calculates the changes as the slinky falls. During this motion, the distances between each mass change, changing the forces acting upon each mass due to the spring tension. For each mass that has a mass above and below, these lines of code calculate the change in momentum and then update the position. I then use these lines of code down here to graph the positions in the model of the top, center of mass, and bottom of the slinky. Due to the fundamental forces at play, you can see that the base of the slinky will, in the model, remain stationary until the distance between all the masses above it are reduced to 0. And that is at this point. This is because the force of tension is equal to that of the force of gravity until there is some sort of change. In this case, a change in the distance between the masses, which results in a change in force and momentum. The net force acting upon the bottom of the slinky is 0 when it's at equilibrium, until the tension or spring force is negligible, and this occurs when the distance between each coil is 0, and then acts as a free-falling object. In the graph, the motion of the center of mass appears to be a parabola. This is because if we treat the slinky as a point mass system, or one complete object, its motion is merely a center of mass, and the only force acting upon a falling object is that of gravity. So the center of mass of the slinky accelerates downward with an acceleration of negative 9.8 meters per second squared. Now let's compare my model to the experimental data I extracted. The trends for the motion of the top and bottom of the slinky are almost perfectly represented, as the center of mass does not show a parabolic trend, like the model predicted. This is most likely due to my inability to accurately place each point of mass on Tracker. In reality, the center of mass changes in a slinky as it's falling, due to the constant changing forces that are acting upon it. The center of mass weight and consequent gravitational force is changing always as the distance between the coils change, and the spring force is also altered as it falls. I was unable to capture this complicated changing of forces, creating inaccuracies in the center of mass position graph. It is most important to note that the base of the Slinky does remain motionless, both in the model and in the experimental results, until the spring force is negligible at the time when the Slinky is fully compressed. The model is able to accurately predict this motion. Would the motion of the Slinky change if there was an additional weight on the bottom? The answer to this question is no, because any additional weight would really increase the equilibrium length of the Slinky. The additional weight force created by the additional mass would be countered by the supplementary tension force to create a net force of 0 once again. The end of the Slinky with the additional weight will still remain motionless until the Slinky is fully compressed.